So next talk is by Peter Sunehag about learning agents with evolving hypothesis classes.
Okay, so this is a joint work with Marcus, the chair session. Okay, so universal induction, solvent induction is providing a solution to the induction problem in principle, but it is incomputable, and more generally, if you're working with truly rich classes of Bayesian method tends to become very costly or infeasible in most cases. So we'll suggest two ways of trying to go slightly downwards from this top-down approach and trying to move towards something that is slightly more feasible to implement in a not too narrow setting. So these two observations come from looking at how science is developing and how it actually differs from universal Bayesian learning or rich Bayesian learning overall, which is sometimes used as an idealized model. Or I'll talk about it will still be somewhat idealized, but it will take two things into account. One, that science is only really considering a few explicit hypotheses at every time, except if one takes into account that one might have some parameter that one is not entirely sure what it is. But if one doesn't count that as different hypotheses, it's only considering a very small number of possible hypotheses at a time. Science also does not develop by considering just complete hypotheses of the world, but it's rather developed by learning more partial laws. For example, Newton's 3 laws and his laws of gravitation did combine into forming the Newton's mechanical universe. So I will make those two adjustments to some of these agents and see what we end up with in a framework. So let's first talk about limited explicit hypothesis classes. So if you consider some initial class M0 of environments, particularly reinforcement learning environments is what I would consider, and a hypothesis generating process that over time adds new environments and that is exhausting some countable class in the limit, for example, all computable environments. And together with an exclusion principle when something has become infeasible. In the deterministic case, exclusion is quite simple because it's just simply contradiction, and I will in this talk only talk about that kind of exclusion to keep it technically simple. But we also worked out the fully stochastic version, but then there are several versions of what exclusion principle one can possibly have. So this way we end up at every time t with some hypothesis class mt of finitely many environments, and this is changing over time. And one could consider having a Bayesian agent, or for example an optimistic agent that I talked about as the last AGI. So here I talk about having the optimistic agent as the one that works with explicit hypothesis classes, both because it's trivial to define for that case. The Bayesian agent, one has a little bit to figure out what I'm going to do with the weights when a new agent is introduced. And also the analysis extends quite simple to this case. And it will also extend very simply to the case of having environments defined by combining laws, which is the next thing I will discuss. At the previous talk I gave about optimistic agents, in the case of having a fixed finite class, the motivation is more explorative than the Bayesian agent, which led to the possibility to have more uniform error bounds than the Bayesian agent is, though when I sacrifice the best in expectation performance. The Bayesian agent has best in expectation performance with respect to its prior. But in this case, we also get away from choosing a prior, but only have chosen a hypothesis class. But we're still going to keep the Bayesian beliefs in this framework, but view it instead of being implicit in a sampling process that generate hypotheses, which I will soon get back to. Let's first review what this reinforcement learning agent, this optimistic agent for a finite class is like. So if you have a class M of finitely many deterministic environments, I'll first talk about deterministic ones, then the agent I talked about last time looks for a pair of a policy and an environment in this class that has a higher expected reward sum, in the sense that you've chosen, for example, discount reward sum is what I consider here. Then the agent follows that policy until there is a contradiction with the environment. And for such an environment, one can prove the following error bound. So an epsilon error, that is when the policy agent is choosing is actually, that is actually following, is worse than epsilon below the optimal return that can be achieved by choosing the actually optimal policy for the true environment. And the maximum number of epsilon errors in total, if the true environment is in the class, that's the assumption here. Then that's linearly depending on the size of the class and on the effective horizon. And then you also have log 1 over epsilon dependence on the accuracy. And this agent can directly be extended to the case when we have a growing class of environments. You have to find it exactly the same way, with this just a slight addition that when we introduce a new environment, we have to check if that is actually promising higher maximum reward than, even for the best policy in that one, than the one we're actually following. In that case, we have to switch before actually seeing a contradiction. So one can extend then also the bound then immediately. So assuming that the truth will eventually be introduced. So if it's in that countable class that we are exhausting in the limit, then it will eventually be introduced. And then we have a constant c plus, and then we have something of the same form as above, where nt is number of environments that have been introduced so far, including the initial ones we had. So in this case, we can actually choose how fast we are introducing new environments. So it has this peculiar flavor that we can actually choose our asymptotic rate, which is somewhat unusual, that when one chooses what rate one can have. But it has this trade-off, so this constant c becomes much larger. If we choose a slow rate for these new introduction environments, we lead to slow asymptotic rate of epsilon errors. But then we get larger c, that is, take a longer time until we introduce actual true environment. So we get a very slow start instead. Okay, the other adjustment we're going to do was, so instead of just considering generic environments, if you just consider a class of, for example, 1,000 environments of any sort that doesn't have any particular structure, any connection to each other, then the bounds I had on the previous slide are really the best where you can ever hope to achieve. But here we're going to consider something that have a bit more of structure. So we instead consider first a class of laws, something to make partial predictions, deterministic partial predictions. So for example, if you have some features, it predict some of the next features, each law. So you have to combine several laws to really have a complete environment. So if that definition, you can from a few laws create a huge class of environments, uncountably infinite if you at every time point has different choices between what alternatives among these environments to combine. For example, I gave an example before, Newton's 3 laws of motion and universal gravitation combines into the mechanical universe. And the key here is that whenever an environment is contradicted, you have contradicted some law. Some law that was involved in defining that environment must be wrong. And then you have not only excluded that environment, but infinitely many environments, all environments that somehow includes that wrong law. So contradiction of a law is contradiction of environments, and we get the same bound except to replace the size of the environment class with the size of the laws instead, which is much better. It's much smaller numbers. Now we can deal with infinite environment. We can also do the extension to growing class just like before. But those results, though nice, were still in deterministic setting, the completely deterministic setting, which is restrictive. But we have one more extension that you can stay within this framework, really, and that is combining these deterministic laws with some correlation between the features in the same time slice. So you predict the things you can with deterministic laws and use correlation from them to the others to define a complete environment, so then take some uncertainty into account. For example, here is an almost tautological law. Getting married at time t means you're married at time t plus 1, at least if that's a short time interval. And if you have this correlation that being married correlates with 43% probability with being very happy, then, well, it might sound like I want to do the dodgy prediction that you just have to get, if you're miserable, just get married and you got 43% probability of happiness. But that, of course, not true. If you're happy before, you have a better chance of being happy afterwards, and the same with misery. But what you're actually saying that you have to form your environments by combining all the laws, deterministic laws you can, and then condition on all of that to make the stochastic predictions for the rest. And if you form a class of environments in that way by combining correlations with a class of deterministic laws, some of which will be excluded after some time, then actually this analysis can go through again. But it demands that truths can be represented within this class. It actually exists in that class. So that means these correlations must have learned really good correlations. Ideally, the true ones, but in practice, probably it's fine to learn very close to true correlations. And then again, we get the same error bounds before. That depends only on the size of the class of laws that you have introduced. And we only have to check for deterministic contradiction. Finally, we need some hypothesis generating process, and here I will not define a full practical procedure, but the ideal property such a process should have is that simpler hypotheses are more likely, or at least a postulate you should have these two, that simpler hypotheses should be more likely to be generated, and a hypothesis aligned well with the observed data so far should also be more likely to be generated. And this, I think, is largely true for science, that one has preference for these explicit hypotheses that are seriously considered, that one has a favor for simpler one, and for ones that has aligned in some way quite well with data so far, and doesn't bother with things that are a complete contradiction with what one is knowing so far. So one can formalize this using algorithmic information theory, as with Solomon induction. And if we can generate any computable hypothesis, which will be the case for that formalization, it's still a form of universal model, where if we have strictly positive probability for any computable hypothesis, so that it eventually is generated. In reality, the simplicity would be really conditional on what's generated before. So we would have conditional Kolmogorov complexity, for example. That would mean the negation of existing hypothesis is again simple, though it sounds unusual that one would introduce a negation of existing worldview. But in fact, if the existing worldview aligns well with data, the negation is going to have a terrible alignment to data. So it's actually not such a fishy thing. So it will not be generated. So it's unclear exactly what a practical algorithm will generate such a thing, which contains some of these Bayesian beliefs implicitly in some approximate manner, some form of inductive logic programming, or some of the series of probabilistic logic or alternatives. Aaron Dansky last year presented some sampling process for sentences from a first-order language, which was an interesting contribution, might be in that direction of creating such a thing. So finally, I must have talked about this is a framework for AI. I can also use it as a slightly less idealized version of science than universal Bayes is, since it contains that only consider a few explicit hypotheses at a time. So problems like this philosophical problem of new theories and old evidence, for example, is resolved by universal induction by removing it, since all hypotheses are considered from the start. In this case, one considers as it is somehow viewed in science, where actually the hypothesis was not suggested until after the evidence was already there. You find dinosaur bone, then you want to predict dinosaurs after, and you say that it's reasonable to predict dinosaurs because you already see dinosaur bones, for example. There also this thing with Mercury's orbit, is a famous example of this. So in this framework, one say that if it's a very simple hypothesis aligned well with old evidence, and these implicit beliefs in it would be quite large, and therefore it would be reasonable, but if it's complicated, it's not. Because one has to see the difference between the prior in this implicit framework towards just a prior that would be on the explicit class, which would be much higher. So you would need that actual implicit prior to be high, which means simplicity must be favored. So you can make a theory more likely by somehow mathematically simplifying, showing it follows from fewer and simpler assumptions. So in conclusion, presenting a way of scaling down universal learners by working with small changing hypothesis classes. New hypotheses should be generated by some process which is implicitly sampling from a universal distribution. We should, instead of sampling full laws, sample partial laws and combine it to full environments. This has been done sometimes in consequent Markov decision process with certain successful algorithms. And I consider it a slightly less idealized version of model of science than the pure Bayesian universal inference. Thank you.